Okay, so let's start. So what did we learn yesterday? We were looking at turbulent flow in a pipe, right? And we realized that something that you do not see, okay, so visually when you see it, okay, you don't perceive it really, that the small amount of roughness, the small unevenness that be there on a pipe can affect your turbulent flow, okay, or in other words the pipe roughness affects turbulent flow. That's peculiar to turbulent flow, and we saw why it is the case, right? We saw that if you look at the wall layer, which is very close to the wall, the thickness of the wall layer is so small that at that scale it becomes comparable to the roughness itself. So in real numbers it could be less than a millimeter, and the wall layer is as that small, and therefore if you really look at the wall layer is not on a flat surface, wall layer is on a surface which is very uneven, okay, and such an uneven, such a complicated geometry could break your viscous sublayer or the wall layer. So that's what where we stopped, okay. So let's just make it quantitative so that you can do calculations. So roughness in turbulent pipe flow. So what we need first, okay, is some way of characterizing the. So one way we need is we need some way of characterizing the roughness, okay. So roughness, how would you imagine the roughness of the surface to be? Very uneven, like for example, if you let's say that's a plate that you are looking at, plate or surface. If you start looking at it under a microscope, you would see something very uneven like that. So you can imagine that thick line that I have drawn is the main thing that you typically see, but if you start zooming in, then you will see that it's very rough, okay, some arbitrary nature. So you need some way of characterizing this roughness, okay, and one thing that you could use, that is typically used, is some length scale for this roughness, okay. So let's say epsilon, will define a length scale epsilon, which is a measure of this roughness scale, okay, roughness length or roughness height rather. You can imagine epsilon is, let's say, some average height or some average or root mean square height, some height, okay, some typical height of the roughness, okay. So that's a scale in which you have these variations. Let's call that epsilon. We can argue that it's not one quantity is not sufficient, maybe you should talk about multiple quantities to really characterize, but we of course do not want to bring in so many things because it makes the analysis complicated. So we want to stick to what we can use practically. So epsilon, let's say, is the thickness that characterizes the roughness, okay, and the quantity that we want to look at is epsilon plus. So epsilon plus would be what? Epsilon divided by, what is the scale that we would use to define epsilon plus? How did we define y plus? Y so we define y plus as y u star by nu, so we will define it as epsilon u star by nu, where nu by u star is some length scale that we have. Why we do that is because we said the thickness, okay, the highest or the thickness of the wall layer in terms of this plus quantity is 5 approximately, right? We said y plus is approximately 5, and up to 5 you see the wall layer. So we can say that if epsilon plus is, let's say, less than 5, what does that mean? That means that if the height of the roughness, okay, is going to be smaller than the height of the wall layer, or in other words height of the wall layer is going to be bigger than the roughness, So in other words, the wall layer will not see the roughness, and therefore if epsilon plus is smaller than 5, then you can say, okay, that my pipe is actually smooth and I don't have to really worry about it, about the roughness. Okay. So we say that epsilon plus is less than 5, we call it hydraulically smooth pipes. Okay. In other words, the thickness of the roughness is smaller than the height of the wall layer. Is that okay? We are just talking everything in terms of this plus quantities, okay, rather than talking about real dimensions. Hydraulically smooth pipes, sorry. If 5 less than epsilon plus less than approximately 7D, then we say it's a transition regime. The transition is in terms of roughness, okay? Because if epsilon plus is greater than 7D, then we call it a fully rough surface. Okay, so epsilon plus is greater than 7D means the wall layer thickness is much smaller than the roughness itself, okay. So then it's so high, so you basically have so it's some classification. So you can say that on one limit you basically have very smooth pipes, and on the other hand you have very rough pipes, and in between, you know, anything that could vary, you basically have a transition regime. And as usual, just like in the flow, here also if things are in between, okay, between smooth and fully rough, calculations are harder, but otherwise, so that's why this classification. Is that clear? So, so what is the what is that we can do in the fully rough region, okay? In the fully rough region, so let's say in this region, the overlap law, okay, basically gets modified. I'll just take it for granted. I'll just write down yu plus is equal to 1 over k ln y by epsilon plus 8.5. So one thing that you can notice is that, see, when we talked about the wall layer, okay, we had defined a y plus, and we defined a y plus as y u star by nu, okay. There was no really length scale that was characterizing it, so we just defined it as y u star by nu. But now when you talk about the roughness, you have brought a new length scale into the system. That new length scale is epsilon. So it turns out that you can define u plus as in terms of a non-dimensional quantity, which is y by epsilon. Okay, everything else, the numbers like, you know, k, 8.5 are all determined from experiments. You can't do much about it. But this is, so the point is that it's still logarithmic. Okay, it's a logarithmic law. The numbers are going to be different, and it's also dependent upon the roughness height. Is that clear? Okay. Yeah, the epsilon is the height. This is for a fully rough surface. More than 30 would be the, what was that? So from y to 30 we had the overlap layer. So what is the question? How do you know that? Okay, yeah, that might be true. So in fact what we are saying is that, so epsilon you are saying is 17. Yeah, so you basically see that the wall layer is so thin that parts of your overlap layer is occupied by the crust itself of the roughness, in some sense, or maybe all the way up to there. So in other words, you are going to see essentially the overlap layer with, yeah, I think that's all it is. I'm not sure whether you can really characterize that structure, because the that graph that we drew was for strictly smooth pipes. So now we are essentially borrowing some of those ideas to talk about roughness. So in principle, some of those numbers might change. That must be what is happening in reality. But if you just strictly borrow it, then we are really into the overlapping. Okay. Yeah, so this is the expression for U plus when you have a rough pipe. So if you know U plus, now you know how to go ahead and calculate the friction factor and relationship between friction factor and Reynolds number, the way you did it yesterday. Shall we try? See, finally, we don't care what exactly U plus is. We need a relation between friction factor and Reynolds number. So since I have given you what is U plus, let's go ahead and calculate what is the relationship between friction factor and Reynolds number. What would you calculate first? Yeah, so you can calculate the average velocity, and then hopefully you will be able to manipulate that expression to give the desired relation. You can go back and finish your calculation. You are expected to get this relation. Okay, friction factor. And what you find is that you wanted to get the expression connecting Reynolds number and friction factor, but you don't see that. Okay, Reynolds number will go away, and the only factor that would remain would be epsilon by d, where epsilon is the thickness of the roughness and d is the diameter. So that's definitely a non-dimensional number, and it looks like at fully rough surface is what we called, the friction factor is independent of the Reynolds number. It basically depends only on the thickness. Basically depends only on the roughness. Yeah. More the roughness. So there is a limit to which it is affecting your, it's disturbing your wall flow. Okay, so see, these things are not independent. For example, the Reynolds number would depend upon your average velocity, which is coming from your flow pattern itself. So you don't really need both Reynolds number and epsilon by d to characterize your flow. It looks like epsilon by d is the only quantity that will play a role within these approximations. Epsilon will be for the pipe. Yeah. Yeah. So that's why it's independent of the fluid flow now. Except, wait, delta P will still be dependent upon the fluid flow. F is a non-dimensional quantity, and therefore it's independent of fluid properties. So you will get an F, and when you connect your F to, let's say, HF and then to your delta P, all the properties, density, viscosity, everything will come. So that's another beauty of non-dimensional number there, right? That you are getting everything independently. Yeah. Yeah. So I'm saying that the logarithmic law is still, so it's experimental observation, and the fact that what we have seen for a smooth pipe can be borrowed. So there are some calculations can be done where you can take different layers and try to match and so on. But for us, it's an experimental observation. All right, so you try doing it. Yeah, so more importantly, it's independent of R. So we have written down so many relations. Okay, it's sort of hard to keep everything in mind. So what people have done is they have plotted all of them. Okay.